Alright, calc class, let's look at another example, finding these critical points or the domain endpoints. So let's look at this graph. So I put it into Desmos, and again I replace y's with f of x just because of the bonus of getting to plug in numbers into this if you use this notation. This is what it gives me. Notice there are endpoints there. I'm going to scroll out just a tiny little bit just so I can click on those. Those are the endpoints of our domain because I am squaring the x coordinates and then subtracting them from 100. So 100, the square root of that is 10 or negative 10. Either of those two that I square, 10 or negative 10, would give me 100 minus 100. And that's the square root of 0. The square root of 0 is 0. But if I made it x any bigger than that, then those numbers squared would be bigger than 100. And I'd be taking the square root of negative. So the implied domain here, the only thing that I can plug into this thing are numbers between negative 10 and 10. And that's why the graph just abruptly ends right there. Okay, and now this thing goes way out of the screen. We've seen that vertical look. So I can plug in something like at negative 5 to see how high up or down this needs to go. I can plug in other numbers and see, do I need to get anything higher than, 100 or something. Negative 100 is what it's looking like. So I can now change my window from, let's do like negative 12 to 12, and then, and then let's go down to 100 and up to 100. And I can see that that's the range that I need to be in. I can see those critical points, right? And I can see those endpoints. So this is some, funky looking function where these are not parabolas. They're asymmetric. But we need to find those critical points. Notice this time it's giving me a decimal. And that usually means, especially with radicals involved like this, it usually means it's a irrational number. Okay, so to be able to find these critical points, or the places where f prime is undefined, we need to find f prime. So we need to take the derivative of this. So don't forget that you can always put, instead of the square root, you can do the 1/2 power, which is what I would do on any of these radical problems. And then notice this is now a product rule problem. So the derivative of this part I'm going to call 2x1 function. So the derivative of it is 2x, and then I'm going to leave this part alone. And then I'm going to add, remember it's f prime g plus f g prime. So now I'm going to add, I'm going to leave 2x alone, and now I'm going to take the derivative of this. And I'm going to need the chain rule. So I'll bring the 1/2 down, and then I'll have this in the parentheses, and then in my new power is going to be negative 1/2. Okay, and then I have to chain on the derivative of what's inside. The derivative of what is inside here is the derivative of the negative x squared part, which is going to be negative 2x. Alright, so there's my derivative. Now I'm just going to clean it up a little bit. So theirs is a little bit cleaned up. I just removed the times dot there. And then half of 2x is just x. And then x times negative 2x is negative 2x squared, that all this will combine to out in front of that. Now this is a negative 1/2. So don't forget that means it's down in the denominator. And now if I want to get a common denominator, if I want to take all of this stuff and put it over this same denominator, it wasn't there before, and I'm making it there, so I have to multiply the top by that same thing. And when I do, I get this 100 minus x squared to the 1/2 times itself, which is just 100 minus x squared. So I don't need a power here anymore because I get to the first power. Now I can distribute that 2 through if I need to, and then combine this into a single fraction. So there's simplifying that numerator, and now I'm subtracting with the common denominator. I can subtract these into a single fraction. That'll put both of these 2x squareds in the top here, make it a minus 4x squared. Now I don't need that because I've combined them into a single fraction. And now we're at the point where we can take the derivative. This is the derivative, and this thing is equal to 0 when the top is equal to 0. So that's one thing I need to solve. But this thing is undefined, right? The square root of 0 is 0. This thing would be undefined when this stuff underneath the radical in the bottom is equal to 0. So let's start with this. If I take this thing and set it equal to 0, that's going to be moving that 4x to the other side. If I divide both sides by 4, I'll have a 50 on this side. So x squared equals 50. That means x is equal to plus or minus the square root of 50. And so the square root of 50 can be simplified to, that's 2 times 25. So leave the 2 in. The square root of 25 is 5. So that's 5 square root of 2. So x could be positive 5 square root of 2, but it also could be negative 5 square root of 2. And that's my places where the derivative is 0. Those are the critical points of this thing. And then these are the places that it's talking about where the domain endpoints where it's undefined. So if I take the x squared and move it to the other side, I'll have x squared is equal to 100, and we know that's equal to plus and minus 10. So x could be 10, x could be negative 10. These are places where the derivative is undefined, but they're part of the original domain. And these are places on the interior where we have critical points. Now, let me do the same trick that we did before. I'm going to say A goes between negative 10 and positive 10. And I'll do that tangent line again. So y is f prime at A times x minus A plus f of A. And these are the tangent lines of the original function. If I move A around, notice there's that tangent line. And at those places, what we talked about before, that's our 5 square root of 2, negative 5 square root of 2 are those critical points right there. But then watch what happens to this graph. I'm going to put A, f of A on the graph. Watch what happens when we get close to 10 and negative 10. The tangent line goes away. Why does the tangent line go away? Because what is that? What type of slope is that tangent line approaching? It's approaching a vertical line. And remember that the slope of a vertical line is undefined. And so at these 2 points, we get an undefined slope. Do we get points on the graph? Yes, they are on the graph. They're part of the domain of the function. But the derivative does not exist there. And again, it's because of that. We're not taking the square root of 0 in the denominator in the original. But because of the power rule creating that negative, we go down in the denominator, and now at those endpoints, the 0 that didn't matter before because it made the function 0, and it's okay for the function to be 0. It's just not okay for a denominator to be 0. That power rule makes this expression right here go down to the denominator, and that's why we are seeing those undefined tangent line slopes at the endpoints. Alright, so anyway, I just wanted you guys to see the visual of that. You don't need to be able to create this visual, but that's the reason why these things are undefined at the endpoints of this graph.